This is the second part of the video lecture for Math 140 for Tuesday, April 28th. And as mentioned earlier, the topic today is applications of the laws of sines and cosines. For our final example, we're going to do a really fun astronomical example. It relates to the orbits of Earth and Venus. It turns out, it's set this way, that the Earth orbits the Sun at 1.0 AU. An AU is defined, it is called an astronomical unit, and it's defined as the Earth-Sun distance. So by definition, Earth orbits the Sun at 1.0 AU. And that's useful because then you can make all the other planets are relative to that. It turns out Venus orbits the Sun at 0.72 AU. So Venus is significantly closer to the Sun than Earth, as I'm sure you knew. Okay, and in this problem, we're going to assume the orbits are circular. In reality, the orbits of the planets are not exactly circular, but they're pretty close. So in this problem, we're going to assume those orbits are circular. Before we ask ourselves any questions about this situation, let's first draw a diagram of this. And so to do that, we'll make a simple diagram. We'll place the Sun right here at the middle. And then I'm going to use different colors for the different orbits. So why don't we draw the orbit of Venus in blue? And so this is the orbit of Venus. We'll make it something like this. If I can draw this as a perfect circle as I can. That's not too bad. That'll be Venus's orbit. And then in black, I'm going to do the Earth's orbit. So we'll draw it like this. That's the Earth's orbit around the Sun. And I'm going to place Earth right here. Okay, and then, Earth is orbiting the Sun, Venus is orbiting, and they go at different speeds. But for the sake of this problem, I'll place Earth right there, and Venus will be various places here. The first part of this problem is, I would like to, and I should mention the distances here too. The Earth-Sun distance is 1.0 AU, and I already mentioned that, and the Venus-Sun distance is 0.72 AU. For the first part of this problem, we're going to ask ourselves, what are the max and min distances between Earth and Venus? In other words, what's the closest that Venus comes to Earth, and what's the farthest Venus can ever be from Earth? Well, hopefully you guys see the closest Venus ever comes is when Venus will be located like this, right here. So that Venus would be exactly between the Earth and the Sun. By the way, I'm also assuming these orbits are coplanar, meaning they're all in the same plane, which is a pretty good assumption. They're not quite coplanar, but we're assuming this is all in 2 dimensions. Okay, so this is Venus right here. All right, and we can start labeling distances here. This distance right here between Venus and the Sun is 0.72 AU, while the distance between Earth and the Sun is 1.0 AU. Okay, so the question is, we want to figure out what is this distance between Earth and Venus. Well, hopefully you guys can see that that's simply the Earth-Sun distance minus the Venus-Sun distance. So the minimum distance, or the closest Venus ever comes to the Earth, is equal to 1.0 minus 0.72, and this equals 0.28 AU. So Venus never gets closer than 0.28 AU to the Earth. Now what's the farthest distance that Venus ever gets from the Earth? Well, hopefully you guys can see that occurs when Venus is on the opposite side of the Sun from Earth. So this occurs when Venus is right here. And in that case, we still have our distances. This distance right here is 0.72. This distance is 1. So the maximum distance between Earth and Venus is equal to the Earth-Sun distance plus the Venus-Sun distance. So 1.0 plus 0.72, and this equals 1.72 AU. So this is the furthest Venus will ever be from Earth. Okay, so that's kind of a fun little part of this problem. It's kind of good to know those distances and how to calculate them. Okay, let's do another part of this problem. And in the second part of this problem, we're going to take the proposition that let's suppose that at a certain point in Venus's orbit, let's suppose the Earth-Venus distance. So if Venus is 1.20 AU from the Earth at a certain point in its orbit, what is the angle between Venus and the Sun as seen from Earth? Okay, so this is the question. If at a certain point in the orbit of Venus is 1.2 AU from the Earth, what is the angle between Venus and the Sun as seen from Earth? Let's think about angles. When Venus is located right here, Venus is perfectly aligned with the Sun. So the angle between Venus and the Sun is 0. Okay, and same for this situation. But there are other times when Venus makes a certain angle between, if you look in the sky, and you could look at the Sun, and you could see Venus as well, you would see that they're a certain angle apart. You can't actually do that with your naked eye, but through astronomical equipment, using astronomical equipment, we can determine that angle. And so what we're interested in is determining what that angle is when Venus is 1.2 AU from the Earth. I want to erase some of these numbers here, some of these lines, and we're going to redraw this situation here. Do that. Redraw this. Apply this diagram to this part of the problem. Okay. So I'm going to roughly position Venus approximately here for this situation to be true. So what this means is, if we draw a line between, and let me draw this triangle in red. If we draw a line between Earth and Venus, as best I can, like this. If I draw a line between Earth and Venus there, this distance is 1.2 AU. Okay. So that's the first part of this diagram. And then what I can do is connect Earth and the Sun, like this. Okay, I know that this distance is 1.0. And then finally I can connect, gosh, this is a hard line to draw. It really is. Straight. This distance is 0.72. Okay, so I know the Earth is 1.0 from the Sun. I know Venus is 0.72 from the Sun. At a particular point in the orbit of Venus, it's 1.2 AU from the Earth. So now I have a triangle, a non-right triangle. And hopefully you guys see, this is an SSS triangle here that I've drawn. Okay, I have an SSS triangle. And I'm interested in calculating the angle between Venus and the Sun as seen from Earth. Okay, what is that angle? That angle actually is just this angle right here, right? I'm going to call it angle theta. If you were standing on Earth and you could look at both the Sun and Venus at the same time, this is the angular distance between the Sun and Venus, how they would appear in your sky. Okay, so I want to find this angle. How do I find that angle? Well, because it's an SSS triangle, I can use the law of cosines, and I can pick. I could pick any side, but there's actually the side that I should pick for A here should be the side that's opposite to the angle I'm interested in. And so I'm going to pick 0.72. Law of cosine says take 0.72 and square it. Okay, that's equal to the sum of the squares of the other two sides, 1.2 squared plus 1.0 squared, minus 2 times 1.2 times 1.0 times the cosine of my angle, which is theta. Okay, I get cosine of theta. So this is now the law of cosines applied to this problem, specifically looking for this angle. Okay, we need to do some arithmetic here. And 0.72 squared is 0.52. 1.2 squared is 1.44. 1 squared is 1. And this comes out to 2.4 times cosine of theta. I want to isolate cosine of theta. And to do that, I can subtract off 1.44, subtract off 1. And this leaves me with minus 2.4 cosine of theta equals minus 1.92. Okay, I'm going to go over here. And now I divide both sides by minus 2.4. So cosine of theta equals minus 1.92 divided by minus 2.4. And this equals 0.80. And finally, what I want to do is find the angle. So theta will equal the cosine inverse of 0.80. And this comes out to 36.9 degrees. Okay, 36.9 degrees. So when Venus is 1.2 AU from Earth, it will make an angle of 36.9 degrees with the Sun as seen from Earth. I want to do two more parts of this problem, so I'm going to erase what I just did here, parts A and B. Okay, I'm going to erase something here. You guys will see why in a second. I'm going to erase this angle. I can do that. Redraw this. Okay. For part C to this problem, we're going to imagine that instead of knowing the Earth-Venus distance, so suppose in part C we know that, we know that the angle between the Sun and Venus as seen from the sky is 30 degrees. Okay. By the way, this angle is called the elongation. It's the elongation of Venus. It's the angle between Venus and the Sun in the sky. Let's suppose we know this angle is 30 degrees. So instead of knowing the Earth-Venus distance, we don't know that distance. We do know the elongation, and we'd like to figure out the Earth-Venus distance. Okay, how do we do this part? So the question is, what is the Earth-Venus distance? In this problem. Okay, well this angle here is now 30 degrees. Okay, that's 30 degrees. And we have a certain kind of triangle now. What kind of triangle do we have? It looks like we have an SSA triangle. And there's actually an ambiguity here. So there's actually two possible distances we could have for this situation to be true. Is that possible? Yes, that is possible, because Venus could also be located right here, right? So at these 2 points in this orbit, we're just going to do one part of this. We're going to assume it's over here. Okay, so how do we do this problem? Well, we can use the law of sines. And I have this angle side pair. And so I get sine of 30 degrees divided by the side that's opposite that, of 0.72. Okay, and I'm interested in getting this angle right here, right, as a first step. What I really want is this distance d, right? I want d, but I can't get d immediately, so I have to use the law of sines to first figure out my angles. So I'm going to try to figure out this angle right here. This equals sine. Why don't we call this angle A? We'll call this angle A right here. So sine of angle A, okay, divided by the length of side A, which is 1.0. Okay, and now we can solve for sine of A. Sine of A is equal to sine of 30 degrees divided by 0.72. And that comes out to 0.694. And if you guys now take the inverse sine of this, you get 44 degrees. So I know this angle here, let me stick with my red here. I know this angle here is 44 degrees. Okay, and now I can figure out my other angle. So now I can figure out this angle, right, has to be 180 minus 30 minus 44, and this equals 106. So this angle right here is 106 degrees. Okay. Basically solving this triangle. That's 106 degrees. Now I'm poised to find the side length d. So again, I'm going to use the law of sines. D divided by the sine of the angle opposite, which is 106, equals, I can pick another pair here, equals 0.72 divided by sine of 30 degrees. And I'll let you guys check the arithmetic on this, but if you do this, you should get d equals 1.38 AU. Okay, so When Venus is 30 degrees from the sun in the Earth's sky, it's 1.3 AU from the Earth. I know this is a long problem, but I want to do one more part of this problem that's quite interesting. So this is a really neat application of the law of sines and cosines to solve an astronomical problem. Okay, let's erase this here. Oops. Let's erase all of this here. I'm just going to erase this all and redraw it. Okay. So we've got let's put the sun in the middle. Sun goes right there. Okay, we've got the orbit of Venus here. As best I can draw it. And let's put the sun more about right there. And now what I want to find in part D is I want to find the maximum elongation. In other words, elongation is the angle between the sun and Venus as seen from Earth. And that angle will vary from 0 degrees, but there's actually a maximum to some other angles, but there's a maximum elongation. And unfortunately, I didn't draw my circle quite right here, so I'm going to draw it a little better. This illustrates this. Like that. The maximum elongation occurs when Venus is located right here. Okay, so if you draw an Earth-Venus line here, let's draw this in red. And again, this is hard to draw these lines like this. Do my best though. Okay, when Venus is at maximum elongation, the line from the Earth-Venus line is actually a tangent line to the orbit of Venus. Okay, because this, as you can see, as Venus goes around, its elongation will be 0 here. It'll get further and further from the sun. It'll go here, but then it will max out. It'll reach a maximum angular distance from the sun, and then as it continues to orbit, it'll come back closer to the sun in our sky. So when Venus is out here, in other words, when the Earth-Venus line is tangent to the orbit of Venus, that's when maximum elongation occurs. So let's draw our lines that connect the Earth and the sun. I'm just going to move over here and draw this like as best I can. Okay, we have this line here. Okay, again, I apologize for the squiggly line. It's just hard to hold it straight. It does look kind of bad, though, doesn't it? Okay. So the thing to realize here is if this line is tangent to the circle, this line right here, the Venus-Sun line, is perpendicular to the tangent line to the circle, right? That's true for any line emanating from the center of a circle. So actually, at maximum elongation, I have a right triangle created. Okay. Now I know these distances. This is 1.0 AU, and this is 0.72 AU. Okay. What I want to figure out is the angle of maximum elongation. In other words, what's the furthest angle in the sky that Venus ever strays away from the sun? How far can Venus get from the sun in our sky? There's a maximum angle. This is it. Okay, let's try to solve this angle. Well, now we don't even need to worry about the law of sines or cosines. We have a right triangle. And now I can write the sine of theta is equal to the opposite side, 0.72, over the hypotenuse, which is 1.0. So this equals 0.72. And now to find the angle, I can take the inverse sine of 0.72. And if you guys do that, you will get 46 degrees. And actually, I should have known that. That's a commonly known astronomical number. So you will never see Venus more than 46 degrees away from the sun in our sky. That's simply the furthest it can drift away from the sun in terms of an angle. One other question is, at this maximum elongation, how far is Venus from the sun? Oh, excuse me, from the Earth. We know it's always 0.72 from the sun. At maximum elongation, how far is Venus from the Earth? Well, let's try to solve this problem. Actually, we just need to find d here. We can use the Pythagorean theorem. D squared equals the hypotenuse squared, which is 1.0, minus 0.72 squared. So 1 minus 0.72 squared. Let's do this out. This is 1 minus 0.5184, which equals 0.4816. And now to find d, we take the square root of this number, and if we do that, we get 0.694 AU. So, at maximum elongation, Venus is 0.694 AU from the Sun, and that's an interesting number as well. Okay, this concludes the video lecture for Math 140 for Tuesday, April 28th. I know this third problem got kind of lengthy, but it's a very interesting astronomical application, and I'll see you guys on Tuesday.